Welcome back. In the last lecture, we finished with the linearization of the Ricci tensor. Our last result was this one. Linearization of the Ricci tensor. I used indices ik for the Ricci tensor, rik, and my summation index was s, 1/2 is h over bar sk plus partial ks h over bar I. Then we had two more terms plus 1/2 eta ik box h bar minus box h a I k, where we recall that h is the trace reversed metric perturbation. We had Gij equals eta ij plus hij and h bar ij was hij minus 1/2 eta ij h, where h was the determinant, no, was the trace, hij. Next, for our Einstein field equations, we need the Ricci scalar. Our Ricci scalar is denoted by just capital R. And we can write here eta ik rik. Some of you might ask, why are we not writing G here? The full definition of the Ricci scalar, of course, involves the inverse metric. If we now use that, the perturbed inverse metric, we showed that this comes with the minus sign. Acting on rik, you see that R here is already linear in H, which means H times anything linear in H will be quadratic. Therefore, this term here is immediately eta ik rik plus terms of order h squared, which is where this expression comes from. We now substitute this in. We have eta ik. We have here a 1/2 partial is h over bar sk plus partial ks there was my s missing, h bar si plus 1/2 eta ik D'Alembert or just box h bar minus box h bar ik. We can now, for instance, raise one of these indices. It's not very nice to write, but probably the best thing we can do. So we have here partial k s h bar sk plus Here this becomes an I, SH bar SI plus 1/2. Remember that eta ik with upper indices acting on eta ik with lower indices gives a 4 because we work in 4 dimensions. Eta is of course constant, so the box doesn't have any action on it, so we can pull the box straight in and then we get again the trace. Therefore here we get minus box H 1/2. These two terms are now the same because I can rename my summation index here to k. Therefore I get 2 partial, and to write it slightly nicer, I'm interchanging the indices here. SK. This is mainly for aesthetical reasons, there's no other reason whatsoever. Here we have 2 minus 1, which means we are left with exactly 1 box H bar. And this gives that the Ricci scalar is partial k, partial s, H bar sk plus 1/2 box H bar. Finally, we can compute the Einstein tensor. Finally, let us compute the Einstein tensor. Our definition is Gij equals Rij. I should really use a k, so I can copy the above result. Minus 1/2 Gik R. As before, note that R, the Ricci scalar, is already linear in H, which means any contributions of G from H will be quadratic in H. Therefore, we can immediately write here a half eta ik R plus higher order terms. And as you know, I leave this out most of the time in this section because we are just looking at the linearization anyway. Now we copy this result from up there. We get those two partial derivative terms and then the two box terms. This means we have 1/2 partial is hsk. We need to swap the indices now, which ensures that the object is symmetric. Then here we have a term with the eta and box H bar. From this we subtract box H bar ik. And now we subtract 1/2 eta ik times r, which is given by this expression. Partial k, partial s, H bar sk plus 1/2 box H bar. You see that there's a factor of 1/2 here and a factor of 1/2 here, and the only combinations will be those box terms. We put this all together, we can do this straight in the next line. Gij, no, Gik is now the following. There's nothing happening with these two terms. We just copy them. H bar sk KSH bar SI. We have here a factor of 1/2, here a factor of 1/2, but there's a minus. What we have hence is a half eta box minus eta box, and there is another half in here, which means these two terms will exactly cancel each other. We then have this term here, so the half hops out, which means we have a minus eta ik, better call this an S, and this an N, partial NS Sn, and the final term that we have is the box term here, minus box H bar ik. And this is the linearized Einstein tensor. And now I want you to recall something that I briefly mentioned in one of the other lectures. So in the Maxwell equations, we used and worked with the Lorentz gauge. Just as a reminder that Lorentz gauge meant that we could choose the A in such a way that it satisfies the equation that the covariant divergence of H vanishes. If you look at these three terms here, you see all of them contain a derivative of the object with a summation. There's partial SHS, partial SHS, partial SHS. Here you have in fact two summations and two derivatives, but what I want you to look at is the single derivative and trace. It's like a divergence. Question: can we find a gauge where partial SHS, I call it, give it a free index we haven't used, A, is 0? If so, this would greatly simplify the linearized field equations. And this is precisely the topic of the next section, making these gauge transformations and explaining what it means to speak of a gauge transformation in this context. From a very fundamental point of view, let me make a little note here on this topic. Note: if we count the number of equations, there's a summation over S which means we have one free index A, which means these are 4 equations in 4 dimensions. And we are now working with almost exclusively a 4-dimensional setting. These are 4 equations. And remember that our xa's are 4 coordinates. A question equivalent to can we find a gauge where this is 0? What we are actually trying to say is can we make 4 coordinate transformations I better put this in a bracket. So can we make a coordinate transformation, which obviously involves the 4 coordinates, so hence the number 4 here. Can we make 4 coordinate transformations such that the 4 equations are satisfied? So I wouldn't have spent so much time on it if the answer to this was no. So the answer is yes. But seeing this is in fact not too easy. So that needs a little bit of work to convince ourselves that this can be done. But from a counting argument, you see, well, why not? That should be possible. Let's see how this is done. This little subsection goes by the name of gauge transformations. And what we are trying to do here, we don't want to find explicitly this coordinate transformation, which will of course be quite difficult. So the question is, we actually want to show that the coordinate transformation exists. And in order to do this, we will do the following. Let us start with a small or infinitesimal coordinate transformation. So what we are doing is we are assuming that our old coordinates xi can be written in terms of some other coordinates x prime minus some function of the primed coordinates, so that the whole right-hand side is a function of the new coordinates. And where I should really give this a different name here. This gets an I. Let's give this a K. Where the vector psi I is assumed to be small at all points. Why is it sufficient to work with an infinitesimal coordinate transformation? The answer is because we are already working with only small metric perturbations. Recall that h is already small. Because h is small, we don't have to worry about large coordinate transformations. Hence, it is sufficient to consider infinitesimal coordinate transformations here. We assume this psi to be small at all points, and then we are making now a few little calculations. If I apply the operator d to this, I just get a dx prime I on the as a first term, and here I have to use the definition of what is df. Well, df is the partial derivative of f with respect to its argument times the argument, and you go through all the arguments. So what we're having here is partial psi I partial x prime k dxk, which is equivalent to saying that partial I partial x prime k is delta ik minus partial psi I partial x prime k. These guys here are our standard transformation matrices, if you so like. Let us apply this to the metric tensor. Recall that the metric tensor is a rank 2 tensor. By definition, G prime AB is partial xi partial x prime A partial xj x prime B gij. This is the definition from one of the earlier weeks in the course. Now we can use this expression and substitute this in here. Delta IA partial psi I partial x prime A, first term, second term, delta JB minus partial psi J partial x prime B, acting on eta ij plus hij. Recall that h is already small. We now assume that the xi's are also small, which means xi, or a derivative of xi, acting on h is again a term of quadratic order. We are only interested in the terms linear in smallness. The first term we get is delta IA, delta JB, eta ij, plus for instance, we can get delta IA, then we pick out one of those derivative terms, which I now write as partial B psi j, and we have here an eta term. Then we have the other combination, so plus minus partial A psi I delta J B eta ij. All the other terms are of quadratic or higher order in either h or psi, but I assume that they're all small. So for instance, you could have a fourth order term where you have partial psi h. That must be third order. So we're only interested in the linear terms, which means here the two deltas, change this to an eta ij, minus the I becomes an A here, and then we can just lower the index down. We get eta aj, and the j becomes an A. So minus partial b psi a minus partial b psi a ab. And of course I forgot the term where delta and delta hit the h. I can squeeze this in here. Which means our final line is that the transformed metric tensor in the prime coordinate system is eta plus h minus partial a psi b minus partial b psi a. Again, notice here the natural appearance of the symmetric combination of those derivative terms. Why is this interesting for us? Well, naturally, we would write G prime AB as eta AB plus H prime IB. Eta is invariant, that doesn't change. If we had started in the prime coordinate system and you went back to the beginning of this section of weak gravity, we would have simply said G prime is eta plus H prime, because the prime is just a label. As we cannot distinguish different coordinate systems, we thus have that H prime AB is related to the original H by this. Which is our first result. This makes also good sense because if we assume that H is small and then we assume the size to be small, then we have ensured that H prime is also small. So that is a good little note. We assumed H and psi to be small. This ensures that H prime AB is also small. Which is another reason why we have to be slightly careful with our coordinate transformations. If we make infinitesimal coordinate transformations, then we can guarantee that this infinitesimal coordinate transformation does not spoil our working assumption that we are working within a context where the metric is eta plus a small perturbation. And we note again that psi a with upper or lower indices, it doesn't matter, has 4 components. which is unsurprisingly the same number as the number of 4 coordinate transformations, because every coordinate xi is changed by xi, so there are 4 xi's. And we are, in fact, after fixing this partial derivative or the divergence of this h over bar, which are 4 equations. Our hope is simply that all of this will work out. What did we do next in our derivation? We introduced, or we had, the quantity h over bar AB, which was HAB minus a half eta AB H. And we showed that this is equivalent to the bar just moving to the other side. Which looks strange, but we showed this explicitly. Hence, if we apply this to our prime quantity, we have the following. We are now interested in, the notation is ever so slightly awkward. I apologize for that, because we now have the trace reverse tensor in the primed coordinates. Some of you might have wondered over here, why did we use a prime? Why didn't we use a hat? Would be a bit easier to read. The problem is if we had used the hat, then at this point we would have h over bar hat, and that's probably even worse than the prime there. Anyway, the formal definition is as before. We have h AB with the prime. We are looking at the definition of the bar now, minus a half eta AB h prime. We just said what this guy was. If I scroll up, we can probably see it. This is here. So we have h AB minus partial A xi B minus partial B xi A minus 1/2 eta AB h prime. H prime is the trace of this, which means we get here h maybe I should do this in turquoise for you. Eta AB h bar AB is those two terms where you need to think a little bit. This is clearly h, and then minus eta AB partial A xi B plus partial B xi A. The eta raises here the A and here the B to an A. In both cases you end up with a summation. This means we can write here h minus 2 partial A A. Changing back to black, minus 2 partial S xi S, because we don't want to repeat the indices A and B. And if we scroll up a little bit, what do we want to do? We want to find a coordinate transformation such that this object here vanishes. We now have an explicit expression for h bar SA in the prime coordinates. What is left to do is differentiate this and see what happens. To make our life ever so slightly easier, I will raise here both indices, and this makes the next line slightly easier to write. Prime AB equals HAB minus, again, apologies for the upper indices here, B psi A minus a half eta AB H minus 2. Nothing happens here because these are both scalars, which implies we can finally compute this object here. This is what we are after. One question you can ask yourself, do I have to keep the derivative here primed or unprimed? Remember that h is itself small. The new and the old coordinates here differ only by something that is small. Hence, the difference between this object and that one without the prime is again only something of order h squared. So I don't have to ever worry about primes of derivatives of small quantities. I'm making a mistake here that is only quadratic or higher order. H over bar prime A B. What do we get? We get a partial A. I'm sorting my terms ever so slightly to make it a little bit easier later. Here is my H AB. Here is my minus a half eta ABH. Let me highlight this in blue. It's this term here and that one. All the other terms I don't do much with, I just add the partial derivative here. First term here gives us minus partial A psi B minus partial A partial B psi A. Here's a factor of 2, there is a half, therefore this becomes a 1. Here's a minus, there's a minus. Those two together become a plus. Therefore I get here a plus partial A partial S psi S. If we now have a look at this term over here, and this term over here, there is an eta AB here. This means we have minus partial A partial B psi A plus partial B partial S psi S. The name of the summation index is irrelevant, so I can change the A to an S or this S to an A, and I have an upper index B here. You see, the position of the partial derivative is different. However, it is not a covariant derivative, it is a partial one, and hence these two commute. I can change this to red now, and therefore these two terms cancel. Which means we have shown this object here is of course again the trace reverse tensor bar AB This is now the guy with the bar, but without the prime, because the guy with the prime is on the left. Partial A is nothing but our D'Alembert or the box operator. Let's write it out again. This is the equation we were after. Let us now choose the following coordinates. Let us choose the psi b's such that box psi b is exactly this guy. If we make this choice, so you start with some coordinate system, you grind through all the procedure, and you end up with those guys. Then you write down the inhomogeneous wave equation and you say, well, I know the values of these four quantities. I will now choose coordinates that satisfy this equation. If I do this in these new convenient coordinates, the h bar prime satisfies the equation that its divergence is free. Let us choose chi such that then equals 0 in these coordinates. You see now that this is a highly convenient choice. In those prime coordinates, the Einstein tensor is given by, we now have to write G, I think it was IK in the barred coordinates. Let's scroll up a little bit. We now have the first term vanishes because of our clever choice of coordinates. The second term vanishes because of the clever choice of coordinates. And the third term vanishes again because we chose very convenient coordinates. And so the Einstein tensor is simply minus a half box times this new h thing. Minus 1/2 box h over bar prime ik. These are our final linearized Einstein field equations. And they're really very simple in many ways. All this is, if you think about this, this is a tensor valued wave equation. And in fact, we have seen an equation like this. Recall lecture 23, where in fact, if you use this box notation, we had a vector-valued wave equation, 4 pi over c jj. I changed this to an I. Which is a vector-valued wave equation. It is not surprising when you look at this equation, you have the D'Alembertian or the wave operator that solutions, especially vacuum solutions of the Einstein field equations, should definitely contain gravitational waves, which is a little bit of a freebie when you work through all this. We will discuss gravitational waves in a bit more detail, and we will study those linearized equation a little bit more. I'll write 2 more sentences and then we're done today, or just a few more notes. So in the presence of matter, we have GIK equals, so prime, minus 1/2 box HIK bar prime equals kappa t. I must add a prime to the t to just make sure that I'm working in the same coordinate system on the left as I do on the right. Somehow this is implicitly assumed anyway. But I'm just making this explicit. And we also recall just briefly that this box operator here, ij partial I partial j, stands for minus dt squared and then our 3 spatial derivatives. Which is exactly the wave operator, which is why we expect gravitational waves to exist. Very last comment is there's obviously no point working with this notation where there is a prime. I could have started the lecture by calling my original coordinates prime coordinates and then working myself towards the unprimed coordinate system, which is of course unnatural because you only put the prime on the new coordinates, not the old ones, unless you know what you're doing, in which case you cheated in the first place. So hence, in what follows, we drop the primes and assume that we work in convenient coordinates in which the linearized Einstein field equations take this very nice and simple form. And because these equations are actually quite nice and will appear a few times more, we can box them up. Your linearized Einstein field equations. Here we expect the final note should really be, say, that the presence of box in these field equations strongly suggests that wave-like solutions can be found this is what I meant when I said earlier that in a sense you could have predicted the gravitational waves first when you looked at the Einstein field equations. They were discovered last for a very good reason. They're incredibly weak and incredibly difficult to find. From a mathematical point of view, they're in fact a very natural part of the possible solutions of the Einstein field equations. So I stop here for today, and then we'll carry on with the section in our next lecture. Thank you very much.